Welcome, everyone. Welcome back to the Green Chemistry Commitment Education webinar series hosted by the Green Chemistry Commitment. We're really happy to start to have a kickoff our webinar series with Dr. Andy Dix at the University of Toronto. My name's Amy Cannon. I'm the Executive Director of Beyond the Nine, a nonprofit organization dedicated to green chemistry education. This webinar series is designed to highlight relevant topics in green chemistry education for faculty and students. Our goal is to provide resources for faculty and students who are looking to adopt green chemistry in their courses and programs. And again, we're happy to kick off our first webinar of the academic year today. Okay, and before we begin, I just want to give you some technical information about the webinar. We're broadcasting live and recording this session, and we'll be posting that by the end of the day today. Therefore, all attendees are in listen-only mode and all lines are muted. If you have a question, then just type it right in there into the question box on your control panel, and the moderators will view it. And we'll respond to as many questions as we can after the presentation. The webinar, again, is being recorded, and it'll be posted right on the link that you see on the screen and also in the welcome box that you see on your control panel. The webinar is being brought to you as part of the Green Chemistry Commitment Program, which is a consortium program aimed at transforming chemistry education, expanding the community of green chemistry practitioners, growing departmental resources for those looking to adopt green chemistry, improving connections to industry, and affecting systemic change in chemistry education. The program is a voluntary, flexible program for adopting green chemistry student learning objectives and for promoting the work that you are currently doing at your institution that can serve as models for other institutions to get involved with green chemistry. So you can find more information at the link here on the screen, greenchemistrycommitment.org, or you can email me directly. As part of the webinar series, we're giving away a green chemistry book at the conclusion of each webinar, and we'll announce the randomly selected winner from our list of attendees at the end of the webinar, and we will send the book directly to you. Today we'll be giving away a copy of Dr. Andy's book. That's the one on the far right here. It's a Springer brief, Green Chemistry Metrics, a guide to determining and evaluating process greenness. So we're really great to have that as the theme of today's talk. So the winner will receive an email from us requesting your contact information immediately following the webinar. So now I would like to introduce our speaker, Dr. Andy Dix. Andy Dix joined the University of Toronto Chemistry Department in 1997. After undergraduate and graduate study in the United Kingdom, he became an organic chemistry sessional lecturer in 1999 and hired as part of the university teaching stream faculty 2 years later. He has research interests in undergraduate laboratory instruction that involve designing novel and stimulating experiments, particularly those that showcase green chemistry principles. This work has led to over 45 peer-reviewed publications in the chemical education literature. He has won several pedagogical awards, including a 2011 American Chemical Society Committee and Environmental Improvement Award for incorporating sustainability into chemistry education, and the 2015 Chemical Institute of Canada National Green Chemistry and Engineering Award. He has additionally edited a book as a resource for teaching green chemistry, green organic chemistry, and lecture and laboratory. And in 2014, he was co-chair of the 23rd IUPAC International Conference on Chemistry Education, which was held in Toronto. And so Andy is going to talk to us today about selected green chemistry metrics for educators. So I'm going to hand the controls over to Andy.
Okay. Well, thank you very much for the introduction, Amy, and I really appreciate the opportunity to speak with everyone this afternoon. Hopefully everyone can hear me okay and see the slides okay. And as Amy mentioned, I'm going to speak a little bit today about some selected green chemistry metrics for educators. I'm going to focus on a certain number in particular and make mention of a few others, certainly not trying to cover everything I might say about metrics today, but focusing on ones that are, to my mind, quite important for teaching green chemistry. I'm an organic chemist by my training, but what I'm saying here today is not really specifically it doesn't have to be related to organic chemistry and green chemistry. I think what I'm saying can certainly be applied to other areas of chemistry as well. So just to try and kick things off then, here's the overall aim for today, to highlight some of these important metrics used to teach green chemistry with connections to industry as much as possible. I think that industry and the connections we can make with industry and students is very important. It's a way that students can really pick up on why we would be teaching green chemistry to them if they are potentially going to enter industry. And industry, clearly, many industries are taking the principles of green chemistry and sustainability very seriously now. So I will focus on some important mass metrics in terms of atom economy, reaction mass efficiency, E factor, and particularly focus on process mass intensity, or PMI, as a metric that perhaps doesn't get as much attention, but it is actually one that is of great interest to the pharmaceutical industry and other chemical industries as well. And my feeling is it's a metric that we should be telling our students about and getting our students to think about calculating PMI values for various reactions that they undertake in the lab. I'll also say a bit about metrics in terms of the nature of substances that students might be handling in the lab or analyzing in terms of literature, syntheses, for example, suitability of solvents and reagents. Industries have done a lot in recent years to not only come up with their own guides for greener solvents and reagents, but also to make them very public. And they've been published in research journals such as Green Chemistry from the Royal Society of Chemistry, and that's something that's really appreciated, and students can use those guides, I think, in a very positive way and interpret them. And along the way, I'd like to profile some educational activities that we have developed here at the University of Toronto. These are some things that we have primarily done in our third year course, which is primarily an organic synthesis course, which has some green chemistry running all the way through it. But I should mention that we're also at the moment in the process of developing modules that we're hoping to incorporate in our first year general chemistry and organic chemistry offerings. So we're looking at U of T really to move beyond just teaching green chemistry to chemists, but also to life science students. And one of the areas that we want to focus on in that regard is mass metrics, and particularly teaching some fundamental metrics to life science students about green chemistry principles. So that's where we're hoping to go this afternoon. Before I get into a detailed discussion of some metrics, I'd just like to share with you something that some of you may have heard before if you've heard me speak at a conference, but the general picture I have of green chemistry is it's like a good relationship, maybe a happy marriage. It's about compromise and decision-making and transparency. And I'm mentioning this again today because I think the transparency side is really important in the context of green chemistry metrics. The idea that we should be considering more than the yield of a reaction when students do reactions in the lab, or they consider them just from a theoretical perspective. They should be thinking about byproducts and everything that goes into a reaction, everything that comes out of a reaction, rather than just focusing in on the product of interest, which is something that we tend to have them focus on. So that's what I mean in this context of transparency and the metrics that I will be talking about. But I think those are three important pillars of green chemistry, if you like, and I will mention something about the decision making a bit later on today as well. So we're familiar, I think, all of us with the 12 principles of green chemistry, and the ones that I've highlighted here in red are really the ones that I'm focusing on today, and I think really tie into the idea of metrics in green chemistry. So some of these are related to the mass metrics, certainly in terms of number 2, for example, incorporating starting materials into the product that we desire, but also thinking about the metrics related to choosing reagents and solvents can be linked to use and generate substances possessing little or no toxicity. So there are only 3 or 4 metrics there that I haven't particularly touched upon or won't touch upon this afternoon, related to energy requirements and designing products that don't particularly have any important toxicological problems related to them. So really we're focusing on a large number of the 12 principles, and many of us appreciate, I think, that these 12 principles are great from a teaching perspective, and students can pick up on them and look at them not just in isolation from one another, but group them together, and we can use them as a way to explain important concepts in green chemistry and sustainability. I thought it would be useful in tying in with an industrial perspective to show you this graph, which is from a publication last year in ACS Sustainable Chemistry and Engineering, which is a relatively new journal focusing in on the role that industry plays in green chemistry and new developments in the field. And this is from a survey of chemical manufacturers who were asked the question, in your opinion, how frequently does your company implement the following principles of green chemistry? So they were specifically asked about the 12 principles, and on a scale of 1 to 4, 1 being never implement the principle and 4 fully implement the principle. And it's interesting to me that the first thing is all the principles are implemented to some extent. There are no principles that score less than 2 on the scale, which is interesting. And there are a couple of, or actually 3 principles that score greater than 3, between 3 and 4 on the scale. The 2 most highly scoring principles are number 1 and number 12. So prevention of waste and inherently safer chemistry for accident prevention. So this says that industries are, we know that they're taking green chemistry seriously, and we know that they are linking their activities to the 12 principles, and that there are, as a principle there, certainly in terms of waste and metrics, in terms of metrics related to waste that the industry is interested in and focusing on, and also the idea of using safer compounds, partly for preventing accidents. So that's an interesting observation, and I'll mention something else from that publication in a little bit of time. So the industry link here is important, and generally we know in chemistry, I like this quotation from Lord Kelvin, to measure is to know, and that's linking in again to the idea of metrics and making measurements and quantifications of various aspects of chemical reactions that students may be undertaking. So with that in mind then, here's a problem from my perspective. Chemists in academia often judge how good, in quotation marks, a reaction is by the percentage yield that is obtained. And I think this starts very, very early on and runs through undergraduate, perhaps into graduate school and beyond graduate school. And really, if we adopt this yield is everything mentality, and we focus on the yield of a reaction as being a very important metric on its own, and that's not really thinking in a green chemistry way. I think that as a laboratory instructor myself, I'm to blame in this regard. I would use yield as a but the point is that yield is not everything. There can certainly be reactions that are very high yielding, but from a green chemistry perspective, looking at other aspects of the reaction, it's not so green after all. So a lot of what I'm saying today is trying to move beyond this idea, teaching the idea that we're very focused on yield and we should be considering actually other aspects of reactions that are very important and feed into green chemistry and sustainability. So with that in mind then, if we think about a few of the fundamental metrics that might be used in undergraduate or college teaching, very, very well known mass metric is the idea of atom economy, and more specifically it's embedded in the second principle of the 12 principles of green chemistry. So atom economy is, as certainly many of us will appreciate, we're thinking about the reaction and its efficiency in terms of the molecular weight of the product that we're interested in divided by the molecular weight of all the reactants that we've used. And it's a useful tool in some ways, particularly theoretically, as one can very quickly judge which reactions are atom economical or non-atom economical. In a very simple sense, we can look at the scheme at the bottom there and say if we have reactant A with a molecular weight of 100 and it is reacted with B with a molecular weight of 200, if our product C has just the sum of those two molecular weights, that's 300, then we have 100% atom economy, and we don't have here any byproducts, and we don't have any wasted atoms going to materials that we're not interested in. Now, that's useful, certainly a very useful fundamental concept. The issue here, perhaps if I just stay on this slide for a moment or two, or a couple of issues that we can mention, is that we are thinking here intrinsically just about the reaction and not everything around it. So this is not taking into account the practical way in which a reaction would be done. It is not considering the reaction yield, for example. It is not thinking about the solvents that are being used or the workup process to isolate the desired product. Some reactions, according to the atom economy notion, will come off very well intrinsically. At the second-year organic level, one might think about the bromination of an alkene, where molecular bromine is just added to a carbon-carbon double bond to make a product that will have 100% atom economy. So will Nobel Prize winning Diels-Alder reaction. For example, aldol condensations will have very high atom economy as well. But there are some reactions that really don't come off particularly nicely. And a good example that has certainly been used in teaching before is the, again, Nobel Prize winning Wittig reaction, where if one considers a typical Wittig reaction and one generates the Wittig reagent as shown in the scheme here, we can see that there are a number of waste products that are generated in the formation of the Wittig reagent and in the Wittig reaction itself. So in the conversion of cyclohexanone to methylene cyclohexane, we can see that actually we're wasting an awful lot of atoms. We have benzene as a byproduct, which is highlighted in red. Triphenyl phosphine oxide is another byproduct. And if we add up the molecular weights along with an inorganic byproduct as well, lithium bromide, if we add up the molecular weights of those three waste compounds, we find that actually our atom economy is only 18%. Now, Wittig obviously was working on this a long time before the idea of green chemistry came around, and I would explain to students that this is not a criticism of the reaction in any way. It gives products that are very difficult to make by the means. But it's interesting to note that such a well-known established reaction does actually waste a lot of atoms along the way. So a nice thing about the atom economy principle is that one can take any reaction that is being taught, both from an organic or an inorganic sense, in lecture, for example, and it can be analyzed, because it's not necessary to actually do a reaction in the lab to calculate an atom economy. One can look at that as a downside of the model, but certainly from a theoretical perspective, it provides a very quick and simple way of looking at any reaction that is being taught. A student can very quickly see where the atoms are going. Are most of them ending up in the desired product, or are most of them actually ending up in a waste container? So atom economy has its usage, I would argue, primarily from a theoretical perspective, and once practical work comes around, there are other alternative improved metrics to consider. One of those metrics that I think is quite nice to think about is the idea of reaction mass efficiency. So reaction mass efficiency can be applied in the laboratory because it is now we're thinking about actual masses of materials that are added in a chemical process. So the expression that we can write here for percentage reaction mass efficiency is the mass of the desired product divided by the total input mass, where we are considering that to be the mass of the reactants that are actually used. So it takes into account stoichiometry of the compound, of the actual reaction. We can also factor in there the mass of recovered materials if any recycling is done as part of the process. So there's an improvement here in a sense over atom economy because actual reactant masses are being considered, and very, very importantly here, the actual product yield is being factored in. So whereas in atom economy there is no consideration of yield at all, the actual yield is built into the percentage reaction mass efficiency calculation. Generally in this calculation, one is not thinking about non-reactant materials, and I would include their reaction solvents, workup, compounds, and so forth. So we are here still focusing just on the reaction. But what is really nice is that this is not a particularly challenging calculation to do for a typical undergraduate experiment if a reaction is being performed. Indeed, it can be calculated very, very easily for any reaction undertaken in an undergrad lab. And I've made the point there at the bottom that students are often very surprised when they do this type of calculation because they get very low numbers very often. So they may, for example, do a reaction that has a very, very respectable yield of possibly 80% or 70%, something like that, which we might say is a very good yield in an undergraduate laboratory. But perhaps they had to use a large excess of one of the reactants to get that kind of yield, and that means then that there is actually quite a bit of waste generated and their percentage RME will be lower, even though they got quite a high yield. So I think it's good for these calculations to be incorporated in the laboratory after a student or a group of students has done a certain reaction. They can go to this calculation. It's straightforward to interpret and understand and calculate a percentage RME. It dovetails nicely with the theoretical atom economy that they may have seen previously in lectures. And of course they can compare atom economy and reaction mass efficiency values that they calculate in the laboratory if that is so desired. So reaction mass efficiency is more helpful, I would say, as it reflects what's actually being done in the laboratory. From an industrial perspective, the historically important green chemistry metric was the so-called environmental, or E factor, that was proposed in the early 90s by Roger Sheldon. And the E factor then, again, people are often familiar and have heard about this, is the mass of adjusted waste for a chemical process divided by the mass of the actual product that was generated. And the adjusted waste there can account for recycling of compounds again, if that actually has taken place. And in industry, of course, this is something that does happen routinely. It's a very quick and easy approach to assessing how much waste is generated. It's a metric that does not focus so much at the introductory level on the type of waste that's produced. So at its most basic level, all waste is considered to be the same. A kilogram of sodium chloride would be considered the same waste as a kilogram of sodium cyanide. At the introductory level, adjustments can be made to it to account for the type of waste. Conceptually, the ideal E factor value then is 0, and the lower the E factor value, the better. If it can approach 0, that's excellent, because that will mean that the amount of waste is minimal, and if it is actually 0, then there is no waste. So it has been around for a long time now as a metric. And Sheldon himself wrote quite a nice review about it in 2007, which is mentioned there at the bottom of the slide, a 15-year retrospective on the metric that he put forward, which is an interesting read. We can describe the E-factor metric as being an end-of-pipe metric in the sense that it is, in some sense, a reactive metric and looking at what is generated at the end of the reaction. And I can make the point also that water is not usually included in the calculation. Sheldon proposed that the very high values would be generated if water was included for all processes. So generally, water isn't included. Now, because of the simplicity of the E-factor metric, then again, it is certainly possible to calculate this kind of thing in the undergraduate lab. And we do this for, or we ask students to do it, I should say, for a Suzuki reaction that we published in the Journal of Chemical Education a few years ago now, and has been one of our mainstay reactions over the last 7 or 8 years. So the reaction is actually shown there, and again, it's a high-impact Nobel Prize winning reaction where the students are generating 4-phenylphenol as the target compound by doing a Suzuki reaction under aqueous conditions, very mild base, and a palladium catalyst. So there are a number of green chemistry features that we can focus on in the nature of the reaction. If students do the E-factor calculation, though, they come up with a very, very high number, which is typically between 400 and 500, depending on their actual mass of product that they generate. So a typical mass that they may form, the reaction is done on a microscale. Typical amount of mass is about 115 milligrams. That comes out at about a 65% yield, something like that on average. Now, it turns out to get that amount of 4-phenylphenol product, you have to use almost 50 grams of material, which is a large amount, and that's incorporating everything in the reaction that is used in the workup and the reaction solvents and so forth. So when students calculate this kind of number, they can compare it to the numbers that you can see there in the table above the scheme, which are typical E-factor ranges for different industry segments. If we were trying to make a comparison here for the Suzuki reaction that the undergraduates do, it would probably be with the pharmaceutical industry, because the product there actually is the backbone of several non-steroidal anti-inflammatory drugs that are commercially available. And the typical E-factor for the pharmaceutical industry then is 25 to 100 kilograms of waste per kilogram of product. So the students' calculated value is a long way away from that, and they're quite surprised by that, and they get an appreciation that there is a lot of waste generated by this pretty typical procedure. You can see that they're going from the pharmaceutical industry to fine chemicals, bulk chemicals, and oil refining. As the product tonnage goes up dramatically, the E-factor goes down. A very nice pharmaceutical example here is the synthesis of Viagra by Pfizer, which is clearly a pharmaceutical, but the E-factor typically for the synthesis of that compound by Pfizer is less than 5. So it goes into the bulk chemical category. It's an incredibly efficient process which has been tweaked over a number of years. So there are some interesting things to talk about with students there in the context of waste. The nature of the waste is not accounted for, but waste is considered to be very important from the pharmaceutical perspective. The metric that I want to talk a bit about now then is one that we're trying to really highlight to students because of its industrial relevance, and I've called it here the gold standard, which is process mass intensity. PMI can be compared with the E-factor metric. In many ways it's similar, but it is focusing on inputs rather than outputs. It is focusing very much on what is going into a reaction rather than what is coming out at the end of a reaction, the waste in the reaction. So we can think of this metric as being a very front-end approach, where the input mass that is being considered here is everything, including reactants, reagents, catalysts. I've highlighted solvents there in different areas, the reaction solvents, workup, and purification. So everything is being thrown in there. And the ideal PMI value then is going to be unity, if you consider this expression, in the sense that all the input mass will ideally end up in the product. And I've mentioned there a few typical PMI values. PMI, as it includes everything, water is generally included in this calculation. And you can see that PMI values tend to be higher than E-factor values in the same type of industry. It's interesting that GlaxoSmithKline, GSK, have targeted a PMI value for this year of 20, which is that number is there in the second publication that is listed at the bottom of the slide from Organic Process Research and Development. So this is a great interest to industry, and it really signals a shift away from an emphasis on waste. It's the opposite end of the spectrum from the E-factor metric that we've just been discussing. So I thought it was worth mentioning or showing you a couple of quotations regarding this metric and how it is considered. The American Chemical Society Green Chemistry Institute Pharmaceutical Roundtable has chosen this specific metric as the key one for evaluating progress towards more sustainable manufacturing. And as such, I would certainly like students to know this and to think about this approach as being a front-end one. So here are a couple of interesting statements about it from a publication there again at the bottom of the screen. So to truly integrate green chemistry and engineering into chemical processes, one has to look at the inputs instead of the outputs. So focus on what is going in more than what is coming out at the end. And focusing on reducing waste helps companies to reduce costs, but focusing on efficiency also enables innovation to create additional value. And I really like that second statement, because it is sort of saying to us and saying to students that if we can control what goes in, we have an opportunity to change the way that we're doing things. If we simply focus on what comes out, we're going to just be doing waste treatment. And that will have maybe less of a positive impact than if we really focus in on the substances that we're using to do a particular transformation, for example. So with that in mind then, what we have from an industry perspective, this is a second graph from the publication I showed you earlier on today. Chemical manufacturing responses to a second survey question: what green chemistry metrics does your company use? And you can see of the three options there on the left-hand side, PMI, E-factor, atom economy, PMI is the one that is used the most. There are other metrics there that are considered to be perhaps more important from an industrial perspective. That's carbon footprint and water usage. And I won't really say anything about those metrics today. Perhaps, though, we should be, as educators, thinking about talking to our students about those metrics and how they're calculated and maybe doing those calculations. The LCA life cycle analysis or assessment there is also considered to be important. That is certainly something I feel that could be introduced to students in the context of a green chemistry course, a dedicated course. It is a very, very complex assessment to do, which has many factors leading into it. I think it's difficult to drop that into an existing course, but maybe somebody who is developing a green chemistry course can talk about a simplified life cycle analysis or assessment within the context of that course. So with that, then, let's move on to think about the waste, what I call the waste conundrum. There's a lady here pointing at a can of soup saying there are too many people counting calories and not enough people counting chemicals, which is quite an interesting statement. And the second little thing there on the right-hand side, too many people are counting chemicals and not enough people are taking chemistry. And probably most of us listening today are thinking that not enough people are taking chemistry, and probably agree with that. But I would kind of take these two little cartoons and blend them together and say that really, from my perspective, not enough chemists are counting chemicals. So we are perhaps not paying enough attention to the amount of chemicals we're using and the type of chemicals we're using, and that is feeding through at the moment a little bit to our students. So one thing that we wanted to do at U of T to try and address this was to design an experiment where students had to count chemicals and count them very, very carefully. And in order to do this, we took a literature reaction from the Journal of Organic Chemistry, which is shown to you on the screen there. And it's not important to focus in on the details of this reaction particularly. It's an Aza-Baylis-Hillman reaction. We can mention a few green features about it without worrying about the mechanism or whatever. It's not important for us. We should be able to look at the reactants and the product of this reaction and appreciate that the atom economy is very, very high. Most of the atoms on the left-hand side are ending up in the product on the right-hand side. And in fact, if you do the calculation, the atom economy is 95%, so it's really, really high. The only byproduct of the reaction actually is water, which is good. There are some catalysts that are used here. There is Dabco and a lanthanum triflate salt. So the catalytic feature of green chemistry is very nice. A greener solvent option is being used. This reaction is done in isopropanol as the solvent, which is a relatively green solvent to be using. From the literature, the reaction yield is 80%, which is certainly good. And that leads then to an overall reaction mass efficiency of 76%. If we multiply the 95 by the 80, then we can say that the reaction mass efficiency is 76%. Certainly energy efficient reaction conditions as well. Reaction is done usually at room temperature, just stirring the reactants together for a week to make the product. There's no heating involved whatsoever. So this is taken from the literature, from J. or Chem, and what we decided to do was to get students to pretty much follow the reaction from the literature with a few changes and get them to analyze the reaction in terms of the masses of substances that they used. And what I've done there is a lot of information. This is just taken from our laboratory manual. It's the procedure that students follow. This will allow them to make about 1 gram of material, which is not an 80% yield. In student hands, the yield is around about 60%. And what I've highlighted there in yellow are aspects of the workup where a lot of material is being used. So a lot of organic solvents, aqueous sulfuric acid, water, dichloromethane, aqueous bases, and aqueous sodium chloride are being used in the workup. And it is the workup that is really contributing here to the mass of the materials that are being used to generate the Aza-Baylis-Hillman product. So students follow this procedure and they perform what I call a student reaction mass inventory. And simply what they are doing here is summing everything up. The components of the reaction and the components of the reaction workup. And here then, if we sum up the amount of material that's used in the reaction, it's about 21 grams, something like that. In the workup of the reaction, though, it's more like 340 grams for a total amount of material to make 1 gram of product, then being about 361 grams. So I've mentioned that the devil really is in the workup. This student reaction mass inventory approach then can be done to any reaction. And I think it's really important to, perhaps if someone runs a laboratory of any type, take one reaction that's being undertaken, doesn't matter what the reaction is, but to go through this kind of analysis to see where the mass is going and to think about what the contribution is. So if one does this for the Aza-Baylis-Hillman reaction, students are then able to reflect quite carefully on how the PMI might be reduced. They calculate a value typically between 350 and 400. So the sort of ideas that they come up with is that perhaps a recyclable extraction solvent can be used as an alternative, although that may introduce an energy cost to get that solvent back. That's the idea of compromise in green chemistry, to go back to my initial statement. So there's some compromise that would have to come in there. Perhaps the amount of aqueous washes or the volume of aqueous wash material could be reduced. Perhaps the aqueous washes could be recycled for a second reaction or given to another student on another day to use for their workup. And importantly, students tend to pick up on the fact that if any catalysts in the reaction were recycled or unreacted reaction components were somehow recycled, that would have next to no impact actually on the PMI. So the big contributions to the PMI are highlighted in the pie chart there. You can see that over half of the mass is water, and there are significant contributions from organic solvents as well. So this is getting students to think more broadly about a process rather than specifics of a reaction. And again, we're moving away from the idea that the yield is everything and that we really often have to focus in on the workup as to where improvements can be made if we are trying to reduce the mass of substances that we are using. There's a reference there at the bottom to a Journal of Chemical Education article that we've recently published on this reaction, if you're interested in having a read of that. But I would stress the point that this is not an approach that is specific to this type of reaction. One could take any reaction that they are currently doing and just embed this kind of analysis into the lab manual to get students thinking about where materials are going when they're actually doing their reactions in the lab. So with those mass metrics in mind, just for the last few minutes or so, I'll say some things about the nature of process substances rather than focusing in on calculating particular mass metrics. So this is where I feel that companies have been very good and transparent in context of green chemistry, because industrial solvent and reagent selection guides have been published, and there are lots of different ones from different organizations, but essentially they work in a similar way to try and rank the greenness of solvents and reagents. So an example here is from Sanofi, the company, where they have a solvent guide where ID cards are set up and different solvents are ranked in terms of their health, safety and environmental hazards, physical properties, cost, and very importantly, the substitution advice. So there are two of these ID cards that are given to their employees on the screen. The left-hand one is for 2-methyl tetrahydrofuran, which is viewed as a useful replacement solvent for, say, dichloromethane for product extractions. And 2-methyl THF then can be indirectly derived from a renewable source, from corn cobs. It can be recycled. Unfortunately, it is somewhat expensive, but the physical and important properties are highlighted there. On the right-hand side is the same chart for DMF, dimethylformamide, which is not such a pleasant solvent from a green perspective. And there's a note there at the bottom that says that should be used only if there is no alternative, such as acetonitrile or other solvents. And there are some red boxes within that ID card which are flags to the user that this is not a preferred solvent to use from a green chemistry perspective. So that's from a solvent angle. And similarly, from a reagent angle, companies like GSK and Pfizer have produced reagent selection guides. And here is one from the GSK approach where reagents are scored for a particular reaction according to their properties, whether they're atom economical or not, stoichiometry, workup, and a life cycle analysis is built in here as well. This is from the GSK reagent selection guide for an alkene reduction, so various conditions to do an alkene reduction, hydrogenation conditions using different catalysts. The reagents are split up into few issues, those with some issues and some with major issues. So we want to stay in the green there. And there are some nice references, as I said. Companies are willing to make this information available, and these can be used, we've found at U of T, in a helpful way from a teaching perspective. So to just give you a bit of a sense of this, we've tried to build these guides into a third-year undergraduate assignment, quite a significant one, where students are asked to propose a synthesis of either a pharmaceutical or an agrochemical or a fragrance molecule that is given to them. So the class is split up into 3 groups. There are 3 slightly different assignments. And students are given a starting material. They are asked to look at a traditional synthesis to morphine, for example, or methyl jasmonate as a fragrance. And they have to consult with the solvent and reagent guides to try and come up with a greener synthesis of the target compound. They also have to answer questions around their synthesis in terms of metrics and do some other analyses as well. So we have run this type of assignment. I can't give an awful lot of detail about it today. We're tweaking it a bit for our 3rd iteration this year, but we're trying to build in use of these guides. They can be used in a simpler way than this, I think, maybe the 2nd year level, just to inform students about alternative solvents and different possibilities, greener options for solvents and reagents. So I think I'm pretty close to running out of time. So here's my, if you like, reiteration of one particular point I touched on earlier, relating to metrics and their importance. So I think that sometimes too many chemists are not counting chemicals, and we need to do a good job of explaining how important it is to look at the whole process with our students and not just focusing on the reaction that they're undertaking, but everything that they are doing. Now, in my discussion of that today, I've said very, very little, if anything, about energy considerations. And I've said nothing about toxicity of products and considerations there. So things are much more complex than I have presented today. But hopefully you can get the sense that there are some really quite straightforward calculations that students can do. They don't necessarily have to do them for every reaction they undertake in the lab. They can see some of them in lecture. That will mesh nicely with what they're doing themselves in the lab. But it's important that they do start thinking about these things and interpreting values that they can calculate, and sometimes comparing those calculations with those in the literature. So just as a final slide, Amy very kindly mentioned that I worked with a student on putting together a green chemistry metrics book. This is a pretty short book. It's only about 100 pages long. It's a primer on green chemistry metrics, goes beyond what I've been speaking about this afternoon. We have published a few experiments in the Journal of Chemical Education on green chemistry labs, and there's one there profiled on the cover last year in decision making. And I worked with a number of people a few years ago on pulling together a green chemistry teaching textbook from a practical and a theoretical perspective, and that's highlighted there on the right-hand side. And if you don't know about it, it might be a good resource to dip into if you're thinking about particularly teaching green chemistry for the first time. So thanks very much for tuning in today, and really glad that you did that, and I hope that you learned something that was valuable. Thanks a lot.
Wonderful. Thanks so much, Andy. That was a great presentation, a great overview of metrics for us. And if anyone's frantically trying to jot anything down off of these slides, we will be posting them on our website. So I'll put the link right in the chat box too. But we do have a couple questions that have come in, and I wanted to ask those to you, Andy, to respond. Sure. And the first one I'll ask is, are there any green chemistry metrics that take into account the relative hazards associated with non-product materials in a reaction?
There are, yes. So that's a very good question, and something that I mentioned briefly earlier on is the idea of a life cycle analysis. And there are publications, and perhaps I can make a publication available, and you can post it or make reference to it later, Amy, where a simple life cycle analysis has been done in a chemistry teaching context, where hazards of materials are factored in along with the kind of aspects I've been talking about today in terms of metrics. So a life cycle analysis is a lot more encompassing in terms of thinking, where have chemicals actually come from, how are they made, what is their fate in the environment, what are their physical hazards, chemical hazards, and so forth. And as I mentioned in the discussion there, that can be done in a very complicated way, and very often is done by industry in quite a complex manner, as it has to be. From a teaching perspective, there are one or two, I think, useful publications in that realm, and I'll maybe forward a couple of links to Amy later on today about that. So it can be done.
Great, great. And another good, this is sort of a bigger picture, this is a great question. Can you please respond to the comment that green chemistry is only important to synthetic chemists? So it's sort of, you know, thinking about this metrics in terms of being geared towards synthetic chemists.
Yeah, that is a great question, because certainly everything I've said today has given the impression that it's only relating to synthetic chemistry, because that's the perspective that we have. It's part of the perspective that we have, and the courses that we teach are in the context of synthesis. I would say that anybody handling materials of any kind can think about these metrics. Certainly in the context of analytical chemistry, I know there's been a lot of concern about solvent use historically using the right type of solvents, so chromatography and recycling solvents. So I think that there is a lead in there with the analytical side of things, where compounds aren't being made, but they're being detected, and the methods for that are using more materials than perhaps is necessary. There are probably other areas of chemistry which don't involve synthesis, but actually involve using things where it's not being looked at particularly carefully, what is being used and how much is being used in terms of compounds. I did have a conversation with a colleague once who was a theoretical physical chemist, and he said, how does green chemistry factor into my work? And I didn't have a very good answer, I have to say. Right. I couldn't really say anything that I felt was reasonable. But you know, most chemists, the vast majority of chemists, handle things. Perhaps they handle chemicals, perhaps they handle machines. Those machines have got to be built. There's energy considerations in operating those machines. So you know, people doing physical chemistry without any aspect of synthesis, or maybe without even handling chemicals, but making physical measurements, perhaps they have to be concerned about the machines and the apparatus that they're using. So I think that can be, what I've said today can be factored into other aspects of chemistry.
Excellent. That's great. I'm going to just quickly announce the winner of the book that we'll be sending you. It'll be Andrew Davis, so you'll get an email from us getting your contact information, so we'll send that right out to you. And then I've got two more quick questions hopefully we can fit in by the end of the hour. One is, you mentioned stoichiometry. Why do you think we typically don't teach stoichiometry beyond general chemistry? This is a great pet peeve that I have personally. We hammer it home in that course and then forget it in organics, and do you think that alone would make a difference in terms of understanding waste generation and some of these other metrics?
Yeah, I totally agree with that. The person that's asked that question has made a really key point. So organic chemists, I think, are historically very poor at balancing equations. Don't think about byproducts. All about what can we synthesize what we want, and can we make a lot of it, and not what goes down the drain, where the waste is. you know, we're using 10 equivalents of this reactant to drive the reaction to completion, whereas, you know, perhaps it would work perfectly well with one equivalent. So yeah, we need to perhaps revisit the reactions that students are doing, looking at the procedures. Maybe they can be done in a more greener fashion. But the very minimum we can, in lectures, organic chemistry lectures in second year and first year, if it's taught in first year, we can look at some reactions and say, okay, let's do a mass balance here. Let's see where things are going. Bear in mind here that the atom economy is quite low because we have these byproducts. We do a pretty lousy job of that generally at the moment. And sometimes actually it isn't even done that well in Gen Chem. I think it could be the whole idea of atom economy, if you want to introduce metrics into first year, and I know most US schools don't teach much organic chemistry in first year. In Canada we do at a number of schools. But general chemistry would be a great place to start talking about atom economy, because students come from high school very often with an idea about stoichiometry and balancing equations. Atom economy would be a new metric for them, and it can be a great way to start off at the beginning of the fall semester some ideas regarding green chemistry. So yeah, I think we can do a better job in organic, and we might think about moving or introducing some things in Gen Chem as well.
Great idea. And I think this is a good one to close the hour here too. If there was time in an organic lab course to introduce only one metric, what would that one metric be that you would recommend for faculty?
Process mass intensity. Yeah, based on what I've said today and the way that my feeling is developed over sort of teaching these metrics for sort of about a decade or so now, I think it would be PMI, because that is giving students a true picture. Atom economy on its own is not. Reaction mass efficiency is better than atom economy. E factor has the many merits, but the downside that you're focusing on waste. And PMI fits the bill for me, because now we're tying in with what industry is very interested in, which is important for students to know, but also we're looking at the whole process, and we're looking at what's going in at the beginning, and we have an opportunity, if we think about what's going in, to make some proactive changes rather than the reactive analysis at the end of the process.
That's great. Okay, that's a great take-home message there. Okay, thanks so much, Andy. Thank you so much for helping us out and giving this webinar. It was fantastic. And please, everyone, mark your calendars for our next webinar coming up in October with Dr. Rich Gurney at Simmons College, and he'll be talking about how he's integrating green chemistry into a research-oriented organic lab course. So it's a really interesting model if you're thinking about integrating research throughout your organic lab course. Okay, thanks so much.